All right, this is section 6.4, comparing linear and nonlinear functions. This first example says complete each table, which we'll look at here in a second. For the sequence of similar rectangles, graph the data in each table, decide whether each pattern is linear or nonlinear. So similar, when we talk about similar figures, in this case rectangles, are the same shape, but they're different sizes. So everything is proportional. Right? So it's the same exact rectangle, but they're different sizes. So everything's proportional in similar rectangles. So let's look at what happens when we adjust the side lengths to make it bigger or smaller. And let's see how that affects the perimeter and then how it affects the area. All right, so the first thing I'm going to do is write a function for the perimeter of a rectangle. And like we've already looked at, we know that we can write P equals 2L plus 2W, 2 times the length plus 2 times the width, and that'll give us the perimeter. Now, here we've got the perimeter or the length being 2x, and we've got the width being 1x. So let me go ahead and modify just for this specific set of rectangles. So 2 times the length would be 2x, plus 2 times the width we just said was x. So if we modify our perimeter function just for this rectangle, then we get P equals the 4x plus 2x, or P equals 6x. And combine our like terms there. So now when we plug in 1 for x, not only are we plugging it in here, we're also plugging it in there. And then so if I use my shape up here, then I would say, well, that's 1 plus 2 plus 1 plus 2, and that's going to be 6. It's a lot easier just to go ahead and put it into the function right there. So 6, and then obviously if we double it, it's going to be 12, 18, and then 24, and then 30. So let me go ahead and graph these points here. First of all, when we wrote x for 1, we got 6. So I'm going to say that's just about right there on this graph. 212 puts us right around there. 318 puts us right around here. 424 and 530. And you can see that these points are all in a line. So when you are talking about the perimeter of a similar shape and you keep adjusting the side lengths, and remember, we're looking at similar figures. So all these rectangles that we're looking at are all the same shape, just different sizes. When you adjust the length and the width, you're going to get a larger rectangle, but everything is still linear, meaning everything is proportional. Remember how we said proportional relationships always start at the origin? Right? So that's a direct variation. So this is proportional and it makes it linear. Now let's look at what happens to the area. Now I know for the area of a rectangle, I'm supposed to do length times width or base times height. In this case, x times 2x would give me area equals 2x squared because I'm multiplying 2 x's together. Well, this definitely is going to be linear because of the exponent there. In fact, we can see what happens when we plug in 1 for the x variable. Obviously, if I plugged in 1 right here, and if I plugged in 1 right there, there'd be 1 times 2, which is 2. And if I plugged in 1 right here for x, I also get 1 squared, which is 1 times 2. Let's go ahead and plug into the formula here, though, for x. I'm going to plug in right there. So 2 squared is 4, times 2 is 8. 3 squared is 9, times 2 is 18. 4 squared is 16, times 2 is 32. And 5 squared is 25, times 2 is 50. And you can see, whereas before we had a linear pattern, plus 6, plus 6, plus 6, plus 6. Here we are plus 6, plus 10. This is plus 14, and this is plus 18. So plus 6, plus 10, plus 14. You can see there's still a pattern there, plus 18. We keep increasing the increasing amount by 4, but it's definitely nonlinear. It's not a constant, it's different each time. So if I graph this, we can see this is not going to be linear. When I plug in 1 for x, I get 2. When I plug in 2 for x, we got 8. When I plug in 3 for x, we got 18. Plugging in 4 got us 32. And plugging in 5 got us 50 all the way up here. So you can see if I graph this, use a different color. When I graph this, I'm going to assume we start at 0. Obviously, you know, if I don't have an x value to plug, if we plug in 0, the area would be 0. So this is going to curve right up there, and this is definitely nonlinear. So what we're going to be doing today is comparing linear and nonlinear graphs. What do they look like? And then how can I tell just by looking at a chart like we just did here, how can I tell by just looking at a chart that it's going to be linear or nonlinear? Okay, so the graph of a linear function is going to show a constant rate of change. Okay, remember another word for the rate of change is the slope, so it's going to show a constant slope. However, a nonlinear function has a variable rate of change. So variable means that it's changing, right? So the rate of change itself is changing. Like in the last problem where it was increasing by 6, and then it was increasing by 10, and it was increasing by 14, then it was increasing by 18. It's constantly changing, which is what a variable rate of change will do. So its graph is not a line. It's going to be, if it's not a line, well, it must be some sort of curve or maybe 2 lines that come together. Okay, this next example says each table shows the height h in feet of a falling object after at t seconds. Graph the data in each table and compare the 2 graphs. So we've got a parachuter who is falling down here in our first example, and a bowling ball that's falling in our second example. So you could probably use common sense and see which one's going to be falling not only at a faster rate, but which one's going to be falling at a linear or nonlinear rate. So let's look at the parachute jumper. Okay, the parachute jumper, when time is 0, they are 300 feet up into the air. So they appear to be counting by 30s on this graph, 30, 60, 90, 120. So 300 is going to be all the way, 300 is going to be up here. Okay, and then so that of course would be our y-intercept, right? If t equals 0, that's x in this case. If t equals 0, then that's the initial height. So that's where they jumped out of. Actually, I shouldn't say they jumped out. That's where they pulled the parachute, which is very close to the ground. Actually, now that I think about that, 300 feet is just a football field's length above the ground. They should have pulled it before then. Okay, the next one is 1 and then 285. So this is going to be 270. There we go, 270. So if I'm looking for 285, I'm looking for something between 270 and 300. So that'd be right between there. So it's going to be right there. And then 2 is 270, so right there. And then 3 is 255, which is going to be right between 270 and 240. And then 4 is going to be 240. So we can see these points are making a line, and it's pretty slow, right? You're only dropping 15 feet every second, which it seems fast, but I mean, you've got a parachute on. You were doing a free fall, so this is much slower. And now you can see it's also linear, so we can make a good prediction for when we would hit the ground. Somewhere right here is where we'd hit the ground at 0, right? And maybe that's after 18, 16 seconds, something around there. This next one is a bowling ball. So let's graph and see what happens to the bowling ball. The first time it says is 0, 300. So we know that's right here. Okay, so they dropped them at the same height. So the parachuter pulled its parachute and the bowling ball was dropped at the same height. And then 1 is 284. So let me go ahead and fill this in. We said this was 270. This little line right there. So 284 is going to be right about here. So far they are pretty similar. And then after 2 seconds, we're down at 236. So this is going to be 210. 236 is going to be right here, maybe. And then 3, 156. Well, this is 150. So 3, 156 is going to be about right here. And then 4, 44. We're all the way down. This is 30. We're all the way down to here. So you can see this graph, I'll do my best here, it's going to look something like this. It's going to curve down, like the bottom side. If we flip the parabola upside down, that's what we got here for our bowling ball. So this is definitely nonlinear, whereas the other function we said was linear. And if you compare the first two, right, after 1 second, they're pretty much in the same spot, right? One was at 285, the other one was at 284, so they're pretty much the same spot. And then the bowling ball really picks up speed, right? So it's still falling, but its speed is increasing to the point where it's obviously after 1 second, it made a huge drop. It jumped over 100 feet to go from 156 at 3 seconds to 44 at 4 seconds. So it's going to hit the ground, I'm guessing, right after 4 seconds, maybe right between 4 and 5 seconds, versus the parachuter who's going to hit the ground at maybe 16 to 18 seconds. In fact, instead of guessing, maybe I should just go ahead and tell you exactly where it hits. We can write a function here for this, right? Y equals, and then our slope, it's decreasing by 15 feet every second. You can see it's going down 15 each time. And then we started at 300. So if I want to know when Y will be 0, right, that would be hitting the ground, Y is the height, I can plug in 0 in to this, and I can figure out when that will be. So subtract 300 from both sides gives me negative 15x. Okay, so I know 15 goes into it 30 twice, so this will be after 20 seconds. So I was a little bit off. It's going to be 20 seconds. But we could actually use a linear function to make that prediction, to find out exactly where it's going to hit, whereas in a nonlinear one, because we don't have a constant rate of change, we have a variable rate of change, we can't do that with what we know right now, at least. You'll probably be able to do that next year, but we can't do it right now. All right, it says, does the table or graph show a linear or nonlinear function? Explain by showing work. So for letter A here, our work can simply be just looking to see if we have a constant rate of change. So as I rise 9, I'm running 2, okay? So that ratio better be consistent. This one, I'm rising 22, I'm running 2. That's not consistent. Then I'm rising 55, and I'm running 2. So this is definitely nonlinear for this one because, and I'll zoom in so you can see a little better, because we are having it's not a constant rate of change, it's a variable rate of change. And then for example B, well, this isn't even a line, so this is definitely nonlinear. So for all of the graphs, you don't really have any work to show. You can just tell by looking at it. But with the charts, you need to show your work. Example C, this is linear. And in fact, we have an equation for this one. We know it has a slope of 0 for a horizontal line, and it has a y-intercept of -2. So our equation is y equals 0x, or don't write anything at all if it's 0x, minus 2. That's our horizontal line. That is the function for this line. And then for example D, we need to check by showing work. It's not rising, it's actually going down 5, so it's sinking 5 and running 7. And it's sinking another 5 and running 7. And it's sinking another 5 and running 7. So this is linear. Not only is it linear, but our slope is -5/7, rise -5, run 7. And our y-intercept, they give you this value right here when x is 0, is 25. So our equation is y equals -5/7 x plus 25. Now, it didn't say you had to write the equation, but I mean, we might as well. It's pretty simple at that point. And yes, this is definitely linear, and I didn't write that. Actually, I did write it for last time. I just need to make sure I write it there. And then example E, this one is nonlinear. I mean, it's made up of 2 different lines, but the slope is not constant. We have a positively sloped line here, and then we have a negatively sloped line there. So the slope is changing from positive to negative. That makes this a variable rate of change, even though it's 2 lines that are coming together. This is actually the graph of an absolute value equation that's been flipped upside down. You'll talk about it next year. And then one last example here for charts. Let's check here. We're going down 4, and we're running 2, and we're going down 4, and we're running 2. Oh, we're going down 2, and then we're running 1. But hang on a second. I said the ratio had to be the same. Going down 4 and running 2 is the same as, if you reduce that, going down 2 and running 1. So this is actually the exact same all the way through. So this one is constant rate of change. So this one is linear. Okay, this one is linear. And then if I want to know what the equation is, y equals, I know my slope is negative 4 over 2, which we said is also negative 2 over 1, or negative 2. And then if I go backwards, and if I rewind this, change colors, if I rewind this and go back 2, and then I rewind this and add 4, that's going to put me at 0, which is my x value. I want my x value to be 0, and that's going to put me at 12. So then my y-intercept then is going to be 12. So now we have the equation of this function. It's linear, and it's y equals negative 2x plus 12. All right, so we looked at graphs and we looked at charts. Let's look at some equations to see if they're linear or not. First of all, this one is just y equals 4.7. And so it is written in slope-intercept form. If I write it like this, right? So just like we had that vertical or that horizontal line in our last set of examples, this one is also a line, so it's linear. And it just has a slope of 0, so it's flat, right? But it crosses the y-axis at 4.7. For this one, this is also linear. It doesn't have a y-intercept. I mean, it does, but it's 0. And then the slope is pi, right? Whatever value is being multiplied to the x is pi, so that's okay. Pi is a number. It doesn't change, right? So this is linear. And then example C, this one is not linear. I know it looks as if the x doesn't have an exponent, just like the exponent was 1 up here, so that's good. This we'll find out in a couple chapters is actually the same as x to the negative first. Negative exponents mean that you have the exponent as a fraction on the bottom, and that makes this nonlinear. So that is so if you see x on the bottom of a fraction, know that's nonlinear. For example D, we can go ahead and distribute this, and this is going to give us y equals 4x minus 4, and that's linear. It's in slope-intercept form. The exponent is 1, right? So that's okay. That's what linear functions are. Example E, we have another fraction here, but the x is on top. That makes a huge difference. If x is on bottom, that means it's nonlinear. So I could actually rewrite this as 4/3 x. All right, and then I know that my y-intercept would be 0, my slope is 4/3, so this is linear. And then example F is definitely nonlinear because of the exponent not being 1 there, so this is nonlinear. All right, in this last example, it says account A earns simple interest. So simple interest is from a 7th grade standard, and simple interest is the equation I equals interest equals principal times rate times time. So that's what simple interest is. It says account B earns compound interest. Now, compound interest has a different equation to find it. You haven't learned about that yet, but let me tell you, it is much more complicated than what simple interest is. It says the table shows the balance for 5 years. So remember, account A is simple interest, put an S there, and account B is compound interest, put a C there. In fact, maybe I should color coordinate a little bit better because it looks like account A is blue. So let me erase this. In fact, I'll erase these lines up here too. Account A is blue, so I'll underline it blue, and it earns simple interest. S there. And then account B is compound, so I'll put C there. And you can see in the graph, the compound interest is starting to curve up like that, so it's not variable. It's nonlinear because it's a variable rate of change, whereas the simple interest is continuing to earn the same amount of money every single year and add that on. So simple interest is definitely linear, where compound interest is not. So every time I plug a value in for t, so basically what they're telling me to do is plug a value in here for t. So t, I'm going to leave that as my variable. But p and r just represent a number. So it looks like my principal is $100. That's the amount you start with. And then my rate, it doesn't tell me what my rate is, but let me just assume it's a number. I'll just call r for rate. T, and then imagine our t being our x value. Imagine this being our x value. Well, this looks a lot like, I'll just give you another one that looks similar to it, 100 pi x. Now, I'm not saying pi is our interest rate, but if I gave you this, you'd say that's linear because 100 pi is what, 314 just about, right? So that's going to definitely be linear, which is why we're seeing this linear pattern up here for simple interest. But compound interest has a different formula, which uses different exponents, and that's why you see the curve there. So linear functions have an exponent of 1, and nonlinear functions have an x exponent that's something other than 1. And then obviously visually, nonlinear functions will curve, or they just won't be a straight line. Okay, that's it. If you have any questions over this, let me know.